My name is Peter Herndon. I'm a back-end developer for Bitly, and I'm going to be speaking today on how we scale Bitly via stream-based processing, or how to stream your way to Webscale. The language is salty, but I highly recommend it. So let's get some definitions out of the way to start with. When we talk about streaming, in our case, we have a public API service that puts events into message queues that are then consumed by web services that are further down in the stack. Each of those web services, microservice, will then potentially add or annotate information and put stuff back into another message queue. All of this happens asynchronously, and for that, Bitly, we are a combined Python and Go shop, so we use a fair amount of Tornado and Go. We have an older queue, but we replaced it with a newer one, which is, again, written in Go. And one important bit on this, which my colleague Sean emphasized in his second talk yesterday, is that we make sure instead of putting command messages into the queue, we put event notifications into the queue. So we post the notification of some event that's happening, and that way interested listeners can decide whether or not they're interested in this particular message, and they can choose how they want to respond. If you're putting a command into a queue, then you are coupling the command with the target of the command. If the command is go process an image, then the command message has to know about processing an image. You're processing an image implementation. So that's a little subtlety there, which is kind of a neat thing to be aware of. Streaming architectures, as we're using them, are sort of a precursor for the Lambda architecture that's been popularized by Nathan Mars. And a Lambda architecture basically takes a stream of events in and splits it into two separate areas. One side goes to basically file HDFS, for instance, and then gets batch processed in usually some sort of Hadoop process. The other side takes the most recent events in the stream and then processes that in order to provide a recency count. So your older, larger stuff gets processed in batch. Your more recent, shorter, smaller amounts of information get processed more or less in real time in your stream side of things. So that's sort of the background for where we're coming from with NSQ. And now let's get into the fun and interesting details. NSQ itself is open source. It is freely available. We have a reasonably sized community of other companies that use the system. And you will find that the main software is at the top link. Then there are the Go and the Python clients and some extra bits in NSQ auth contrib. Jahaya, by the way, is our VP of engineering. So let's start with the server bits. We have a number of bits and pieces that come in the box. And we're going to go through each of them in turn to show you what they can do and how they all fit together. There are clients, and there are, more importantly, utilities, which make life really, really, really pleasant. On the server side, the first two building blocks, the major building blocks, are NSQD and NSQLookupD. And to illustrate how they interact, I'm going to take you through building a basic web app. In Python, like I say, Bitly's a bit of a Python shop. This would be Django, and your database might be Postgres, or Flask and Postgres, or Tornado and Postgres. Maybe I have a little bias showing. So you have your web app, and you realize that you have a bottleneck layer. So having written your web app in a way such that the architecture is reasonably stateless, you can scale it out by simply running more instances of the web app, which is great. So that eliminates the first bottleneck, the web app layer, which simply exposes the second bottleneck to your users, which is your database. So you add a caching layer, which works for a while, but the DB requests still wind up taking too long, so you replicate, and then eventually you get even bigger, and so you start sharding. And that's great. That allows you to scale horizontally for a ways and allows you to handle lots and lots of traffic. But at some point, you get to the realization that while you've eliminated the bottlenecks in terms of handling numbers of processes, numbers of concurrent users, what you haven't handled are perhaps the actual request response times. Individual requests take too long because they're doing too much work. So you wind up adding a message queue and a worker system. In Python, again, this is going to be Celery. The backend might be RabbitMQ or Redis. The web app sends messages to the queue. The queue transmits those messages to the worker. The worker pulls the message off and processes the message and then writes the results to either the database or the file system, or it does whatever it's going to do. Now, in a distributed message queue system, NSQ, imagine instead that your worker continues to write results to whatever it's doing. The web app continues to post event messages to a queue local to this particular web service. Yes, there's a reason for the outline. But the worker is listening to a queue running on an entirely different server. So already we have two queue instances. This allows us to build an infrastructure which winds up resembling this at sort of a small scale. Now, the interesting bit here is that when you have this kind of system where you have a worker listening to a queue, in NSQ, the queue itself can wind up being actually several different queues. You can scale that horizontally as needed. So how do you find the topic of events that you're interested in listening for? You find that by NSQ lookup D. NSQ lookup D is going to tell you, it's a central registry of all of the topics and channels, and so your client is going to talk to NSQ lookup D, say, hey, where are all the producers of a given topic, say the spam API or whatnot? And NSQ lookup D will reply with a list of NSQD hosts and ports. So the client will then attach to each of those NSQD instances and consume messages from them all. A given topic, now this is kind of neat, a given topic does not exist in the NSQD system until the first time that a writer to the queue writes to a given topic on the queue. So at that point, so you have a client connecting to NSQD. It says, hi, I am going to publish to the spam API topic. NSQD says, oh, okay, and registers that with NSQ lookup D. A worker in another service looking for that particular topic asks NSQ lookup D, replies with the address of all of the workers, makes its connection, and registers a channel. Now, what's a channel? Well, channels are our way of horizontally scaling workers. So you have NSQD, it is publishing events in a given topic, spam. You have 3 workers in this case that are all connecting to the spam counter channel. And what this gets you is, say, 10,000 messages are coming through per minute or whatnot, or per second, on the spam topic. They wind up getting divided between all of the available clients, all of the queue readers that are connecting to it. So each worker in this case will get 3,333. So you can add as many workers as you want, and they can scale horizontally as you need. You can add as many NSQD producers on the spam topic as more things write to a given queue, or on another server you have them writing to another queue instance. So at that side, everything is horizontally scalable as well. Now, the other neat part is that you can have multiple channels for any given topic. What this winds up doing is 10,000 messages per second, 10,000 messages go to spam counter, 10,000 messages go to NSQ to file. 2 different channels, all getting duplicate copies of the messages. This allows you to do different things, but all on the same source of information. So how do we keep an eye on all of this? NSQ admin is a system we wrote also in Go, which comes in the package. And by telling NSQ admin where your NSQ lookup Ds are, it will talk to your NSQ lookup D instances. And by the way, you should be running, say, 3 to 5 per data center. And that will give you a very nice management administration interface. Here's a list of some of our topics. As you can see the rate per second, you can see the number of messages, you can see the queue depth. If you click into one of the topics, you get a list of the NSQD producers for that particular topic and their messages. If you click through into one of those, also note, you get some really nice controls here. You can delete the messages, pause the topic, delete the topic. That's kind of blown out. Oh well. Yeah. And then if you click through into one of the NSQD hosts, you get some very nice statistics that you can't see at all on this page. But at the top, imagine, if you will, that there's a series of sparkline graphs that show you memory pressure, garbage collection runs, and basically all of the stuff that you need to see to be able to tell how well any given NSQD process is doing. On top of that, you also have a further list of all of the consumers for that particular NSQD host. Now, how do you control access in and out? For that, we have a simple utility, PyNSQAuthD. It is it's a little Tornado application that we've written that basically takes a CSV of users, topics, and whether they're allowed to publish or subscribe to that given topic. You point your NSQ lookup D and your NSQDs at PyNSQAuthD, and it will tell you whether or not your client is actually allowed to make that particular connection. It's pretty simple. It fills our needs, but it's pretty easy to. It's pretty obvious how you would go about extending it. You could have that talk to LDAP or Active Directory if you are going that particular route, or any other way you wanted to do it. So the next question then is, how do we make use of all of the little things that are available? For that, we'll take a deeper look at the PyNSQ client, which is here. In our own use, when we build a microservice within the Bitly infrastructure, we implement a queue reader for the service, and that is basically how our streaming architecture is implemented. We have little microservices, each responsible for whatever it is they're doing, and they will have a queue reader. They listen to something upstream. They will often publish something downstream, or they'll do whatever work they're supposed to do. Here's an example queue reader for our spam metrics. It's more or less the same code you saw before. This is the executable part. There is a validate method which looks like this. It's very straightforward. Basically, it says, is this message of interest to me? Does it have some sort of properties that I'm interested in? If so, return true. If not, return false. If it does return true, then the message gets passed on to the message handler, which here is defined. All it does is it accepts the message, it counts some bits and pieces, it increments some counters in stats D, and then it finishes by calling NSQ message finish. What this does is it tells NSQD, it acknowledges that this particular message is finished. If NSQD does not receive this finish message within, I think the standard timeout is 60 seconds, that's configurable, then what NSQD will do is it'll take a given message and put it at the back of the queue for redelivery. So there's message retry. Okay. So again, here what we have is we have written our own reader class, which wraps PyNSQ bits and pieces, and in the reader itself, we're telling it where to get the topic and what channel that it should be writing to. So let's talk for a little bit about some of the things that make life comfortable in the world of NSQ, which are some of these utilities. NSQ tail pretty much does what you think it does. It allows you to attach to a given NSQD topic, and it spits out all the messages to standard in, standard out. If it spit them to standard in, that would be entertaining. Yeah, so it basically lets you see what's going on. You can also, stick that through a pipe and do interesting bits, any Unixy command line sort of thing that you can imagine. NSQ to file basically takes that same concept, and instead of going to standard out, it goes ahead and writes it to a given file. We use this very extensively. This is our backup service. We basically save every event that comes through to S3 in our case. The neat part about this is that if you have queue readers, each with their own NSQD and all of this, and you are streaming these messages as they come through and you are writing them out to S3, you have an historical record for each event that you can trace through from the very beginnings of your system, each of the way through. This is neat because if your section over here for spam counting, for instance, or better yet, spam analysis, is missing some stuff, and you say, hey, we need to go back and we need to reanalyze all of this stuff, and we need to publish all of this for our analytics, then what you can do is you can take 2 NSQ, you can re-implement your logic, you can take all of the events upstream, use 2 NSQ, and 2 NSQ reads from a file of distinct JSON messages and dumps them right back into a given queue. So backup and restore effectively. NSQ to NSQ is a really handy utility because what that will do is replicate from one NSQ instance to another. We use this to do basically multi-data center replication. If we have queues or topics, particularly, that need to be not in our colo but instead over in EC2, then we'll use NSQ to NSQ to get them over there. NSQ to HTTP is also a handy little thing. What it does is it connects to an NSQD source, and for each message that comes through, it shoves that source out, makes an HTTP call, get or post, your choice, with the body of that message. So if you have a source of NSQ messages, but don't really want to bother writing your own client, then you can simply write a web server that handles JSON. So let's talk about some of the features to start off with. It is distributed. There's no single point of failure. Well, you could run one single NSQD and one single NSQ lookupd, but that would be a bad idea, and that's kind of your fault. We do strongly suggest you run multiples of NSQ lookupd, say, like I say, 3 to 5 per data center, and then run NSQ lookupd specifically, 3 to 5 per data center, and then NSQD, at least 1 per service, possibly multiples. It is horizontally scalable. It is encrypted. It uses TLS by default. It has built-in statsd integration. If you have statsd running somewhere, you just tell it where in the configuration, and it will shoot out events. Boom, 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 boom. It is written in Go, and this means that it's fairly easy to deploy. If you've run any or worked with Go, you'll find that it compiles to a binary. It is a static binary. All the bits and pieces are linked in, which means you can, assuming you have a single architecture, you can compile once and shove that binary out to all of your systems, and you're done. It's also fairly easy to administer. Like I say, it comes in the box. So some of the trade-offs. Messages are not durable. NSQ is memory-based by default. The interesting little bit about this is that, again, it's configurable, but there is a high memory watermark, so that if you have a 32 gig cluster, you can tell NSQD not to use more than 20 gigs of RAM, say. And if you get more messages backing up in a given queue than will fit inside of that memory, then they get written to disk. So any overflow gets written to disk. The interesting bit about this is that this allows you to tune your durability. You can set that threshold to 0. You will have a really, really slow NSQ implementation if you do that, but it is possible to do, and that way you get a lot more durability. Trade-offs, caveats, SSDs, you can make things faster under the hood, but generally we don't run that way. Messages are guaranteed to be delivered at least once. For instance, in the case where you have a client pull a message off and it starts processing the message, and say you have a network partition between the client and the NSQD. The client may call NSQ message finish, but that message won't ever get back to the NSQD. NSQD will say, oh, hey, I never received an ACK on that message. I'm going to requeue it. This means that your client code needs to be either idempotent or capable of doing deduplication. It also means that you're going to have unordered delivery. It's possible for something to come through the pipe, get requeued, and more recent stuff, older stuff, it's possible. It will happen. That's in contrast with Apache Kafka. I understand. I'm not personally very familiar with Kafka, but my understanding is that it does somehow guarantee ordered delivery through probably Zookeeper, I think. Eventually consistent discovery. This is kind of an interesting thing. If you have, say, 3 NSQ lookupds, and you have an NSQD come up with, hey, I've got a new topic, it pushes that notification out to, say, 2 of those NSQ lookupds. You get a network partition. The third one does not know about it. You have clients that still somehow have connectivity to all 3. It's possible to get into a state where a client does not know about one particular producer, one particular NSQD producer, simply because it's asking the wrong NSQ lookupd, and there's a network partition and it can't get to the rest of the lookups. However, assuming that partition heals, then your system will eventually wind up discovering that new NSQD producer and start to consume messages from it. This basically is the set of trade-offs that define NSQ and how we use it, and that lets us create architecture that looks like this, where each of these little points is a microservice. And that count is reasonably accurate, but growing. And everything winds up getting connected by messages that go from one service to another. This allows us to scale to about 3,000 requests a second at the moment, without too many issues. And as needed, like I say, we can scale further. It's just a matter of, at that point, a question of how do you handle the latency from the very first event to the very last service that's consuming your messages. So a streaming architecture, in our case, makes it easy for us to build new services, easy to scale individual components horizontally. It's durable in the face of single component failure, and it is distributed, or can be. There are some things that you need to think about, though, and cast a very skeptical eye. For one thing, you need to monitor. In my best Steve Ballmer impression there, which is not terribly good. If you don't monitor, you don't know when things fail. If you don't know when things fail, you can assume that they're broken. How does your application handle failure modes? How do things fail? If an individual component breaks, do you simply just rewrite your web UI to work around that? Failure monitoring, pretty binary, things either working or not. Measurement, on the other hand, metrics allow you to show the range, see the range of operation, and this is why we love some StatsD, some graphite. It allows us to see when things are getting a little too high or too few messages coming through, all of which are indicators of potential problems. Timeouts. We've run into situations where we've had to patch HTTP libraries to add connection timeouts, DNS timeouts, things that happen a lot. A slow network is pretty much the same as a failed service, and you need to more or less treat it that way. That is NSQ in a nutshell. Here are the URLs again. A little bit of photo credits, and now I'm open for any questions if anybody has any.
Do you feel like you're competing with the AMPQ standard?
More like just ignoring it.
Fair enough.
That's kind of the thing. One of the questions that I will fairly frequently get is, hey, have you guys heard of Q implementation X, and did you look at that? And for things like Kafka, which weren't around when we wrote this, then, well, no. On the other hand, things like RabbitMQ that have been around for years, yeah, we looked at RabbitMQ, and I think there was actually probably a bit of a shortage of folks who were comfortable enough running Erlang that they didn't want to get involved with that. So they decided to write their own.
Would you say that was your biggest reason? Or was it another shortcoming of RabbitMQ on top of it?
I'm not sure there was a shortcoming. I know that in practice, I have run into that dreaded problem where RabbitMQ just locks up. Yeah. And it's not terribly hard to figure out why and how to fix it, but I think at the time when they were first looking at it, the folks who had run into the problem and figured out how to fix it hadn't actually put those notes online yet. So it's a history. Yeah. Yes. That is certainly one reason, yeah. I mean, we write stuff to file in part to make sure that we have a historical record so that we can do actually the replay as needed. That's actually something that we wind up doing a lot of. When you're working with large quantities of messages, if your analytics system just fails for a little bit, then you've lost an hour's worth of analytics data. How do you get that back? In a stream-based architecture, if you do not have a system in place for just saying, okay, I'm going to go grab a bunch of stuff and replay it through and regenerate the necessary numbers, then you're kind of out of luck. It is something you need to account for at design time.
And each message goes to S3 by itself?
More or less. I think we're probably, if I remember correctly, I think we're batching them. We're writing a bunch of messages to a file and then putting that file into a bucket.
So AMPQ does this decaying back off, like decaying retry.
Mhm.
Any reason not to, or would you write that into an SQ?
It is there.
All right, so
Yeah.
the S3 writing part is part of the NSQ feature set. So you say you back up the messages to guarantee replayability.
Right. Yes. Mm-hmm.
So and that's just a manual process you do.
Oh no, not at all. Not at all. It's automated, but we do it using the NSQ to file utility.
Gotcha.
Yeah. Mm-hmm. That's all. Sir. Are we backing up all the topics? No, not all of them. I mean, it's a judgment call. I think there are some that are considered, throwaway that we really don't care about, or that are cheap enough to regenerate that if we needed them, we would just take ones from further upstream and replay. We really have. I don't know, maybe 10 or so really distinct topics that we produce that are actually significant. Within each of those 10 topics, there's going to be several stages where they go through. For instance, we'll have a redirect of a bit.ly short URL back to the long URL, and that's sort of the initial decode event. But then we'll have a correlated decode where we've annotated that with extra cookie information. Then we'll have a device decode that takes correlated and adds device and platform info. It'll go through that stream and it'll get enriched through as we go through. That particular one is our primary bread and butter, so we're backing, we're NSQ to file on that pretty much every step of the way. But there's, it's a mix, it's a judgment call.
When you said that you usually put events on the queue, does that mean that there might be a subscriber that will do something in response to that event and then trigger more events?
So the question is, we put events in the queue, are there subscribers that will react to that and produce more events? And the answer is absolutely yes. Absolutely yes. That is kind of the heart of the system, is that each individual worker will, at a given level be responsible for the business logic in terms of deciding, for instance, in spam particularly, we get a lot of folks who try to encode stuff that the rest of the internet probably is better off not knowing about, and or that are simply, abusive folks doing silly things. And at the very top level there, that's one of the first sessions that, first sets of queue readers that it goes through. It will make a decision at that point whether to further process it with enrichment about, going out and extracting data about the actual source URL or not. I mean, if it's junk, it's not going to bother queuing up that kind of information. So yeah, very much so. It's a logic stream that very much splits out into different places, yes.
And the reason why you do events is an event is a fact that something happened and that's never going to change.
Right. That is exactly it. That is 100% it, yes. A command can change. Maybe I want to do something, maybe I don't. You don't want that in the message. You want that at the message reader level, making the logic there. always, always, always just put events in, event information.
Would an event be read by another reader?
Yes.
And if so, when does it get deleted? Besides,
Well, in a number of cases, what we'll have, like I say, for our decode stream, which gets enriched, one of the things that we'll have is we have a fairly chewy system called Clickatron, which does all of the counting of these decodes for each of our individual users. So ESPN, one of our customers, has their account. We need to count clicks on ESPN links in particular. Clickatron will take care of that. It's not an enrichment service, it's an analytics service specifically, and it just counts the clicks, and that's a dead end for that particular branch of the decode stream. On the other hand, that's just one channel. You've also got other channels. You've got, for instance, we're working on a system called Count von Count, which is counting unique cookies off of the decode stream, which is doing some enrichment analysis and aggregation, and that's a separate channel off of the same topic. So yes, decodes will wind up getting counted and stored in a database over here. Unique cookies will wind up getting analyzed, aggregated, and counted in a system over here. They may or may not produce, depending on the service, they may or may not produce stuff downstream from that. It's entirely, what you actually need your system to do. Any further questions? Anything? Okay. Thank you very much, folks.